Welcome to TalkTensors. Today we're doing a deep dive into some really fascinating research. It's about potentially shaking up neuro-symbolic learning.
Yeah, it tackles a big challenge. Getting these powerful AI systems, the ones that combine neural nets and symbolic logic, to learn effectively without needing tons of labeled data.
Exactly. Imagine AI that can figure out complex rules and reason, but, without us having to spoon-feed it examples. That's the promise we're looking at today.
It's a significant thing because traditionally these neuro-symbolic systems, or NeSy systems, they've been pretty hungry for labeled data.
Right, which really limits where you can realistically use them, doesn't it? Getting all that data label is often a huge bottleneck.
A massive one. So this paper we're digging into offers a potential path forward, a way around that dependency.
Okay, so our source is a recent academic paper really getting into the weeds of this unsupervised NeSy challenge. What we want to do is unpack their main ideas, understand the context, how this fits into the bigger picture, and maybe even explore some, future possibilities.
Sounds good.
So where should we start? What's the absolute core concept here?
Okay, the central piece, the innovation, is what the researchers call verification learning, VL for short.
Verification learning.
And it represents a really interesting shift in thinking. It moves away from learning based on explicit input-output labels towards learning based on, verification. Checking if things make sense according to a set of rules.
So not, is this the right answer, but is this answer consistent with the rules?
Exactly. See, traditional unsupervised NeSy approaches often struggled. Without labels, it's harder to ground the symbols, the solution space gets massive, and systems tend to find these shortcuts.
Shortcuts, like finding a loophole that fits the rules but doesn't show real understanding.
Precisely. Like our car engine analogy from before, just listening might lead you to weird conclusions if you don't know the underlying mechanics.
Gotcha.
So verification learning uses unlabeled data, yes, but it combines it with a verification function. Think of this function as embodying the knowledge base, the rules of the domain.
And it uses this function to check if the symbolic representations the system generates actually conform to those rules.
That's the key. It verifies the satisfiability. Does this potential interpretation satisfy the constraints laid out in the knowledge base? And critically, this check doesn't require pre-labeled examples.
So it's more about internal consistency with known rules rather than matching external labels.
You got it. They actually formalize this whole thing as a constraint optimization problem, a COP. The goal is to find the symbolic representation that, one, best fits the perceptual input from the neural network part, and two, satisfies the constraints in the knowledge base.
Okay, that makes conceptual sense. But hang on, if the system is just generating potential symbols, surely there could be like a ton of possibilities. Checking them all against the rules sounds, slow. Correct. Extremely slow.
Ah, yes, the combinatorial explosion problem. That's a very real concern. Checking every single possibility exhaustively would be computationally infeasible for most interesting problems.
So how do they get around that?
That brings us to the second key piece. The dynamic combinatorial sorting algorithm, or DCS.
DCS, okay, what does that do?
Think of DCS as a smart search strategy. It doesn't just randomly pick potential solutions to verify. Instead, it tries to prioritize the ones that seem most promising based on the neural network's initial guess or score.
So it ranks them somehow,
Yeah.
Puts the likely candidates at the front of the queue?
Exactly. It dynamically sorts these potential solutions based on an optimization goal, essentially, how well they fit the input perceptually. Then it verifies them in that order.
I see. So you check the best guesses first, hoping to find a valid solution quickly without needing to explore the entire vast space.
Precisely. It brings the computational cost down significantly, closer to what you'd expect for a constraint satisfaction problem, rather than full optimization.
And how does it manage that sorting efficiently?
They use a data structure called a heap. It's very efficient for keeping track of the highest scoring solutions that are still waiting to be verified. And there's a nuance here. Initially, they explored an assumption that different parts of the solution might be independent when scoring them.
Which might not always be true in complex reasoning, right?
Right. They found that for many NeSy tasks, a property called monotonicity is actually more crucial.
Monotonicity. Remind me.
It basically means that improving one part of a potential solution doesn't suddenly make the whole thing worse, according to the scoring function. If making a piece more likely generally points towards a better overall solution, that's monotonicity.
Okay, so it's a slightly more relaxed, but perhaps more realistic assumption for these kinds of problems.
Yeah, it gives the DCS algorithm more flexibility to work well across different tasks.
Now, you mentioned shortcuts earlier. The paper really highlights this as a major hurdle in unsupervised NeSy, right?
Oh, absolutely. It's a huge issue. Because you don't have explicit labels guiding the learning, there can be many, many ways to satisfy the constraints that look correct on the surface, but are actually nonsensical.
They gave that addition example, didn't they? Like learning plus uncle plus could lead to 0 plus 0 plus 0, 0, 0.
Exactly. That 0 plus 0, 0, 0, 0 technically fits the structure symbol plus symbol, local symbol, but it's obviously not the intended arithmetic. In a supervised setting, you'd have labels correcting that immediately. Unsupervised, it's a valid though useless solution.
A shortcut. So how does VL deal with that? Finding a valid solution is one thing. Finding the intended meaningful one is another.
Good question. This is where their third main technique comes in, distribution alignment.
Distribution alignment sounds statistical.
It is. The core idea is to leverage the fact that symbols in real-world systems often have a natural frequency or distribution. Think about digits in arithmetic or pieces in chess.
Okay, so some symbols just appear more often than others naturally.
Right, so distribution alignment encourages the model's output distribution of symbols to match this expected or prior distribution.
How does that help avoid shortcuts like the 0 plus 0, 0, 0, 0 thing?
Well, if the system starts overproducing zeros, for instance, because that's an easy shortcut solution, the alignment mechanism penalizes this deviation from the expected distribution, where all digits should appear with some frequency. It nudges the model back towards generating a more balanced, realistic set of symbols.
Ah, I see. It acts as a kind of self-correction, pulling the learning process towards more plausible solutions based on expected frequencies.
Exactly. And if you don't actually know the true natural distribution for a task,
Yeah.
you can often just use a uniform distribution as a starting prior, assume all symbols are equally likely. Even that simple assumption can help prevent the model from collapsing onto a single trivial solution.
So verification learning to find consistent solutions, DCS to do it efficiently, and distribution alignment to avoid meaningless shortcuts. That sounds like a pretty comprehensive approach.
It really is. And they don't just stop at the methodology, they also provide a theoretical analysis.
To understand the fundamental limits.
Precisely. They wanted to figure out what unsupervised NeSy, augmented with this distribution alignment, can theoretically achieve. What are the boundaries?
That sounds really valuable. What concepts did they use there?
They introduced the idea of the symmetry group, the verification function.
Symmetry group. Sounds like abstract algebra.
It kind of is. Think of it as all the ways you can swap symbols around in a solution without violating the rules defined by the verification function.
Okay. Like swapping two identical numbers in different boxes in a valid Sudoku grid. The grid is still valid.
Perfect example. That's a symmetry. The symmetry group tells you which symbols are inherently indistinguishable from the perspective of the rules alone.
So if the rules treat two symbols identically, the unsupervised system might confuse them.
That's the core insight. They define orbits, groups of symbols that can be swapped for each other under these symmetries. If a symbol is all alone in its orbit, it's called a fixed point.
And fixed points are easier to learn correctly.
Much easier, because the rules give them a unique role. The difficulty comes from symbols that belong to larger orbits. Based on this, they define a task-induced upper bound on error.
An error bound. Like the best you could possibly hope to achieve.
Sort of, yeah. It's an upper limit on the error that's inherent to the task structure itself, specifically due to these symmetries among non-fixed point symbols. It tells you how hard the task is fundamentally for unsupervised learning.
Can you give examples of how this plays out?
Sure. Their Sudoku example is great. Because of the high degree of symmetry, swapping identical digits, rotating the board, etc., the task-induced error bound is actually 100%.
Whoa, 100%, meaning you essentially can't guarantee solving it correctly purely unsupervised?
Theoretically, yes. It suggests it's fundamentally very hard because so many symbols are interchangeable according to the rules alone.
Okay, what about an easier case?
Addition. In standard addition, almost all symbols, digits, the plus sign, the equal sign, are fixed points. Swapping 3 and 7 drastically changes whether an equation is true because of this low symmetry.
The error bound is low.
0%, theoretically. Meaning, with enough data and the right setup like VL, unsupervised learning should be able to solve it perfectly.
That makes intuitive sense. And chess. You mentioned chess earlier.
Chess is interesting. There's a kind of partial symmetry. For instance, A rook's moves are a subset of a queen's moves. You could potentially map a rook perception to the queen symbol and still satisfy some movement rules.
A one-way inclusion.
Right, but here's where the distribution alignment helps. Queens are much rarer than rooks in typical chess positions. This natural distribution helps the model distinguish them correctly. So when factoring that in, they argue the task-induced error for chess also approaches zero.
So the theory connects the inherent structure of the problem, symmetries, with the learning approach, distribution alignment, to predict potential performance limits.
Exactly. They even wrap this up in a formal generalization error-bound theorem, which combines this task-induced error with the empirical error observed during training. It's quite rigorous.
Okay, theory is great, but did it actually work when they tried it out? What about the experiments?
They did extensive experiments, and the results look, well, pretty compelling.
What tasks did they test on?
4 rule-based tasks, all tackled in a fully unsupervised manner. Addition, like M-missed digit addition, sorting lists of digits, matching sequences, and a simplified chess task focused on legal moves.
And the result?
Across the board, VL significantly outperformed existing unsupervised and even some semi-supervised NeSy methods like deep probe log, deep stock log, and others they compared against.
Really? Better than methods that had some supervision?
In many cases, yes. On addition, for example, using just the binary signal from the verification function, does this equation hold, yes or no? VL got near 100% accuracy, beating supervised-only baselines.
That's seriously impressive, just using the rules themselves as the learning signal.
Really highlights the power of leveraging constraints. They also did ablation studies, basically, removing parts of their system to see what impact it had.
But like what happens without DCS or without the distribution alignment?
Exactly. They compared different scoring settings for DCS and looked at the effect of a final test time correction step. These studies help confirm that each component of VL contributes to the overall strong performance.
And was it fast? We talked about the computational cost earlier.
That was another positive finding. On the addition task, they showed VL was very time efficient, even faster than some methods that pre-process the knowledge base. The DCS algorithm seems to really work in practice, reducing the number of verification steps needed.
Faster and more accurate without labels. That sounds like a win-win.
Pretty much. And good news for other researchers, they've open sourced their code on GitHub so people can build on it.
That's great to see. So stepping back a bit, how does this fit into the broader history of AI? We've seen swings between different approaches over the decades.
Absolutely. You can see this work as part of a larger trend, trying to bridge the gap between, classical rule-based AI, often called System 2 thinking logical, deliberate, and modern data-driven deep learning, System 1 intuitive, pattern-based.
Early AI was all about those rules, right? Trying to encode human knowledge explicitly.
Yes, symbolic AI. Great for structured reasoning, but brittle, hard to scale, and struggled with messy real-world perception. Then deep learning exploded, amazing at perception tasks like image recognition, but often lacking in robust reasoning, common sense, and interpretability.
And NeSy aims to combine the strengths of both.
That's the goal. But as we've discussed, the supervised versions often hit that data bottleneck. Complex reasoning might require an exponential amount of labeled data, which is just not feasible. Plus, there's the issue of label leakage. Sometimes the labels inadvertently give away the answer in ways that don't reflect true reasoning.
Like in that M-missed addition task, maybe the position of the digits gives a clue, not just their values.
Exactly. So verification learning comes along as a novel way to harness the power of rules and constraints, a hallmark of symbolic AI, but within a flexible learning framework powered by neural networks, and crucially, without needing direct labels. It sidesteps the massive data needs of supervised NeSy and the brittleness of purely symbolic systems.
It feels more like, well, how humans sometimes learn or check their understanding. We don't always rederive everything from scratch. We often check if a new observation or idea fits with the rules and patterns we already know.
That's a really good analogy. Like a mechanic hearing a weird engine noise. They don't necessarily simulate the entire engine's physics. They check specific conditions. Does the timing sound right? Is the pressure okay against their internal model of how it should work? They're verifying against known constraints.
Right, which naturally leads us to think about what could come next. Time for our novel notions segment.
Let's do it. So, building on this idea of verification.
Yeah.
The paper assumes we have a predefined correct verification function, a given knowledge base, VKB. But what if that's not the case?
You mean, what if we don't know all the rules perfectly?
Exactly. Or what if the rules are too complex to write down easily? So, novel notion number 1. What if the system could learn the verification function itself?
Whoa, okay. Learn the rules and the perception simultaneously, still without labels for the symbols.
That's the idea. Imagine the system interacts with an environment, or it gets a few demonstrations from an expert, and from that it has to infer both the underlying symbolic representations and the rules governing how they interact the verification function.
That sounds incredibly ambitious. How would that even work?
It's definitely pushing the boundaries. But you could perhaps imagine using techniques from meta-learning, where the system learns how to discover rules or constraints. Or maybe reinforcement learning, where the reward signal isn't about achieving a specific goal state, but about the internal consistency of its learned world model, its learned VKZ.
If that were possible, the applications seem huge. Domains where rules are implicit, like social interactions, or incredibly complex, like biological processes.
Right. Understanding systems where we can't just write down the physics easily, but there's a huge challenge, of course.
Stability.
Reliability. Absolutely. How do you ensure a learned verification function is actually correct and robust? How do you stop it from latching on to spurious correlations or incomplete rules in the environment? That's a major hurdle.
So, probability-wise, where would you put this? Near term? Far future?
I'd say low probability in the immediate term. It's a big jump in complexity. But maybe medium to high probability in the longer run, especially as research in areas like unsupervised representation learning and meta-learning continues to advance. It feels like a natural, albeit challenging, next frontier.
Learning the rules of the game while learning to play it. Fascinating. Okay, what's number 2?
Novel Notion 2 plays with the nature of the verification itself. Right now, it's pretty binary. True or false. Satisfied or unsatisfied.
Okay.
What if verification wasn't absolute? What if it was probabilistic? Imagine a system where the verification function outputs a degree of certainty or a probability that the symbolic representation satisfies the rules.
So not just yes, no, but probably yes, or maybe violates rule 3.
Something like that.
Yeah.
Think about real-world rules. They often have exceptions, ambiguities, or rely on incomplete information. Legal reasoning, medical diagnosis, things aren't always black and white.
That makes sense. How would that fit into the VL framework?
Well, this probabilistic output could potentially integrate with the DCS scoring mechanism. You wouldn't just prioritize solutions that score high perceptually, but also those whose verification yields a high probability of being consistent with the potentially fuzzy or uncertain rules. It might draw inspiration from probabilistic logic approaches, but applied in this verification context.
So it could handle uncertainty more gracefully, both in perception and in the rules themselves.
That would be the goal. Useful in noisy environments, or where rules are more like strong guidelines than rigid laws.
What's the overlooked implication or challenge there?
Defining what that degree of certainty actually means and how to learn it reliably is tricky. How does uncertainty from the perception module propagate through to this probabilistic verification? It's not trivial.
And the probability for this one?
I'd place this at maybe medium probability in the relatively near future. There's already a lot of work on integrating probability and uncertainty into neural and symbolic systems. Applying it specifically within the VL verification framework seems like a plausible next step, especially for domains grappling with ambiguity.
Very interesting possibilities. Okay, let's wrap this up.
Right. So the big takeaway from our deep dive today is that this verification learning approach really does present a promising direction for unsupervised neurosymbolic AI. It tackles that core dependency on labeled data head on.
Yeah, but shifting focus from matching labels to verifying consistency with rules.
And that could unlock NeSy for many more real-world problems where getting labels is just too hard or expensive. The theory they developed gives us a way to understand the limits, and the experiments show it works really well in practice on several tasks.
A solid foundation for future work in this area, for sure. And for anyone listening who wants to get into the nitty-gritty, we'll definitely link the full paper in the description.
Absolutely. It's worth a read.
So a final thought to leave you with. If AI systems can start to learn the rules of reasoning implicitly, just by observing and checking for consistency, what does that imply about how much explicit structure is truly necessary for building intelligent systems? Something to ponder.
A great question.
Thanks for joining us on this deep dive with TalkTensors.